All right, we have example B, or example 2, on our algebraic techniques. And this time, we have 2x cubed minus 4x squared, and then all over 2x squared. So let's take this to the limit. We're looking at our limit as x approaches 0. So if we look at plugging that in, again, direct substitution, not good. We get denominator 0. Can't do that. We could graph this thing and see what happens. But for this week's notes, our goal is to use some factoring. So let's see what happens when we factor the top. Well, let's see, we've got, we can say 2x squared. We can pull an entire 2x squared out of this whole thing, and then x. So 2x cubed times what gives me 2x cubed? So 2x squared times x gives me the first term minus, well, what gives me from 2x squared, how do I get to 4x squared? So just minus 2. So I've actually, that is a way of factoring something where I just say 2x squared out gives me that, let's see, 2x cubed, 4x, okay. And then the bottom, we can't really factor anything. I'm just going to leave it as 2x squared. But we can see that there was a reason for that. Coincidence? I don't think so. What we need to do is look and say, oh, well, if I have a factor on the bottom that gives me 0, but that factor is also on the top, that gives me a hole. So by definition, in your notes, that would give us a hole in the graph. So let's look at that. Here it is. In fact, I didn't even factor that out. I just left it as the original. I could have rewritten that, gotten the same thing, but take a look. We want to know as this graph, remember our limit as x approaches 0 is what we're trying to find. Well, it looks like it's a continuous line. If we look a little closer, we find at 0, x is undefined. So there is in fact a hole here at 0, but the good news is finding our limit as we approach 0 from the left, as we approach 0 from the right, they both look like they're coming to -2. Right, so if I were to do this and say g of 0, my value, it says right here, is undefined. If I put 0.001, it's really close to -2. Or if I go negative 0.001, it's giving me -2.001. So we can kind of confirm this graphically. Our goal is to see if we can get this algebraically to show that our limit is -2. Not that one. Let's see. We need to find, let's see. Well, what I did in the first example, and I can do this again, is we rewrote this. In essence, we're taking out the whole. We're taking it out. What I mean is if we divide top and bottom, like those two terms reduce to 1. Because if I have a number on top and a number on bottom, they're the same, they reduce to 1. So this whole thing is really like looking at x minus 2. Well, let's see, is that right? Well, let's see, x minus 2, there it is. And if I turn purple off or on, you can see that that's exactly the same thing. So graphically, this is the same thing, but what's nice is if I reduce that and just say x minus 2, I no longer have a hole because I'm never at any point going to be dividing by 0. So if I want to do that, I can say, okay, well, let's find the limit. Find the limit as x approaches 0 of x minus 2. Well, that we can plug it directly in, right? 0 minus 2 is -2. Okay, algebraically, we just proved that as we did graphically, as we're approaching 0 from the left, approaching it from the right, doesn't matter, we get limit is -2. So I'm going to finalize this. We say our limit as x approaches 0 of the original 2x cubed and there we have it. Okay, so you always rewrite it as, you can rewrite it with the whole missing, like you removed the whole, or maybe you have an asymptote. But in the end, you want to make sure you finalize your answer as the original function. So there it is. We'll get to example number 3 here momentarily. So thanks for watching.